Hi, my name is Neha Yandamori, and this is my lab report for Lab 1 of Physics 2211. So in this lab, we will be observing the motion of an object in constant velocity and developing a computational model using Python to fit the object's motion. Then we will compare the model's predictions of the motion with the observed motion on tracker. We will be using Newton's second law in this lab, which states that a change in velocity over a change in time is equal to the total pushes and pulls on a system divided by the mass. And this is the formula for that. And we will also be using the velocity update formula in this lab, which is basically the same as this formula but just rewritten in a different way. The object I chose to observe is a tennis ball, using the principle of Newton's first law, which states that an object in motion will remain in motion at a constant velocity, and an object at rest will remain at rest unless acted on by an unbalanced force. We will assume that there are no net interactions acting on the tennis ball. So here's another important formula, which is the position update formula. So this is tracker, and it is what I use to keep track of the observed position versus time of the tennis ball. The observed position that we're interested is only from frame 24 to frame 43 because that is where the ball appears to be undergoing constant velocity. And I set the origin at the center of mass of the ball. So let me play the video. So as you can see, the ball is moving in the positive x direction, and I kept track of the position of the center of mass of the ball frame by frame. And this is the graph that was plotted. It's a position versus time graph. And as you can see, the slope is positive, meaning the ball was moving in the positive x direction. And then the graph is also linear, meaning that the ball was under constant velocity as well. So these are all the data points that it took, and at time equals 0, the position was this. So this was the initial position. It took the position all the way up until 0.633 seconds. So in order to develop our computational model, we need to have the initial position, which I have right here, and we also need the initial velocity. So taking the first two position vectors and their times, we can find the average velocity using those two initial position vectors, because average velocity is equal to the change in position over change in time. And we can use that as our initial velocity since the velocity doesn't change. So these are the first two position vectors, and then this is the initial / average velocity. So here's the code for our model, and here I put in the mass of the ball, and I also updated the initial position and the initial velocity of the ball, and I changed the time over here. And then for these two equations, I updated them to match the velocity update formula and then the position update formula. So if we run this program, it looks like this, and the graph is also positive and linear. So here's the Google Sheets for my lab, and I have the time in the A column, and then I have the observed position from tracker in the B column, and then in the C column is the predicted position by the computational model, and here are all the data points. And then over here we have the graph of the predicted versus observed position versus time, and they are pretty similar, the two graphs, but they do deviate from each other over here at the end. But this shows that the model is a pretty good representation of the observed motion of the tennis ball. So the ball was able to maintain moving at a constant velocity after the initial push I gave it, and this is based on the observed values we got from tracker because the observed position versus time graph was relatively linear. Comparing the predicted graph with the observed graph, it shows that they line up pretty well, but the ball actually ended up having a slower velocity than what was predicted by the model. One reason for the deviation between the predicted and observed graph is because we made the assumption that there are no net forces on the tennis ball. We do not know all the forces that were acting on the tennis ball, and there could have been a small unbalanced force acting on it from different environmental factors, causing it to deviate from the predicted position. So what if we decided to change the orientation of the axes in tracker? If the axes were changed in tracker, then the tennis ball would have been moving in the negative x direction rather than the positive x direction, and the slope of the graph of the observed position versus time graph would have been negative. However, the actual slope value / magnitude would have stayed the same. And is it possible for us to say how many pushes and pulls are added together to give zero net force? No, it's not possible for us to know how many pushes and pulls are acting on the system we're observing, but we do know that there is a gravitational force from the Earth and a normal force from the floor onto the tennis ball, which can cancel out, but there can be a number of other forces acting on the object. Thank you.